In this video, we'll talk about the central limit theorem. This might seem like an intimidating phrase, but it essentially formalizes a phenomenon that we've already observed. First, recall that in any data analysis, we're using data from a sample to learn about some broader population of interest. But sample data provide mere estimates of the trends in the broader population. Further, different samples of different data can produce different estimates, some accurate, some not. And unfortunately, we can't know for certain whether our estimate is one of the accurate ones. This is where sampling distributions come in. A sampling distribution describes the degree to which our estimates can vary from sample to sample. Hence, it helps us understand the potential error in a sample estimate. Consider an example. Suppose we are interested in using sample data to estimate the population model of the relationship between y and x. That is, y equals beta 0 plus beta 1 x. As we've observed, different samples will produce different estimates of this model, these estimates being denoted by beta hat 0 plus beta hat 1 times x. Notice that these different sample estimates, represented by the unique black lines here, have a variety of slopes, beta hat 1. The variability in these slopes is captured by the sampling distribution. Though most of the slopes fall slightly above 2, they range between roughly 0.5 and 3.5. Next, suppose we had a crystal ball and could know what was going on in the population and could then compare our actual population model and slope, represented here by the red lines, to our sample estimates. Though each individual sample estimate is incorrect, we observe that the estimates are scattered around the actual population values. That is, the sample model lines are scattered around the actual population line, and the slopes of these sample models are scattered around the slope of the population line. Another way to think about this is that though some samples produce unlucky estimates, the average or typical sample will decently approximate the truth. Now, this thought is somewhat comforting, but there's a snag. That whole exercise was hypothetical. In practice, we only take one sample of data. Thus, we can't know what the actual population model is, and we can't know what estimates would be produced by different samples. That is, we can't know the actual sampling distribution. Thus, in order to understand the sampling distribution, hence the potential error in our sample estimates, we must approximate the features of a sampling distribution. There are two common approaches to this approximation. First, the central limit theorem, or CLT, makes theoretical mathematical assumptions about the sampling distributions, assumptions that don't always hold in practice. Second, bootstrapping uses simulation, not mathematical theory or formulas, to approximate features of the sampling distribution. This approach will typically give similar conclusions as the CLT, but it's more generalizable to estimation in settings outside the STAT 155 context. Thus, in this video, we're going to focus on the CLT. Again, this theorem formalizes a phenomenon that we've already observed. Mainly, recall that the sampling distribution of our collection of sample slopes was roughly normally distributed around the actual population slope, represented by the red line. In fact, so long as our sample size is large enough, that is, so long as we have enough data, this is a common phenomenon. That is, the collection of all possible sample estimates will tend to be normally distributed around the population value that we're trying to estimate. More formally, let beta hat represent a sample estimate of some population value, beta. Then the sampling distribution of all possible estimates beta hat is normal. Specifically, the possible beta hat values are normally distributed around beta with some standard deviation or standard error. The standard error here is what we call the standard deviation of our sample estimates beta hat, and it's calculated from our sample data using a complicated formula. I'm not going to include that formula here. Stepping back, let's consider the implications of this theorem, or why we should care. First, the fact that the possible beta hat values are normally centered around beta implies that, though we can't know how our sample estimate compares to the actual population value beta, we can know that the typical sample estimate falls close to beta, or in the range of the normal model here. Hence, though not certain, it's unlikely that our estimate is way too small or way too big. Next, the standard error or standard deviation among all possible sample estimates beta hat measures the degree to which these estimates vary from sample to sample. More specifically, it measures the typical difference between a sample estimate and the true population value beta. However, notice that this difference represents an error in an estimate, how far an estimate beta hat falls from the true population value beta. Thinking about it that way then, the standard error of beta hat actually measures the typical error in a sample estimate, hence why we call the standard deviation a standard error in the first place. In turn then, the standard error gives us what we wanted all along. It gives us a sense of how much error might be in our sample estimate.